Complex numbers. I'm sure you're familiar with the real number system, which includes rational and irrational numbers. Now we're going to add a further set of numbers. You must know about the unreal or imaginary numbers. We're now going to combine them with the real numbers to give the set of complex numbers. The definition of a complex number is a plus bi, where a and b are real and I is the square root of -1. Square root of 3 times square root of 3 is 3, so square root of -1 times square root of -1 is -1. Square root of -1, which means the number which when multiplied by itself gives -1. Well, we're multiplying it by itself, so we get -1. Now that is I times I squared is -1. Try these little exercises yourself, remembering that I behaves in the same way as any other variable. So as in 3 times x is 3x, we have 3i. 3x times x is 3x squared, so therefore we have 3i squared, but I squared we know is -1. This one's exactly the same as the previous one, really. 3i squared, -3. Here we need to square the 3 as well, so it's 9i squared. Give you -9. Write that as I squared times I. And I squared is -1, so we get -i. Don't assume therefore that all odd powers of I are -i, as you'll see in a short while. 2x times 5x squared is 10x cubed, so that is 10i cubed, and we've found that I cubed is -i, therefore we're going to have 10 times -i, -10i. I to the 4. And here we mustn't assume that all even powers of I are -1, because if we split this into I squared times I squared, we end up with I -1 times -1, which is +1. So in fact it seems that any power of I which is divisible by 4 gives you +1. Any power of I which is even but not divisible by 4 will give you -1, which means any power of I one more than a power not even power not divisible by 2 will give you -i, and I to the 5 will give you I. Just be careful when you work with them. So now we deal with I the same as any other variable. So if we look here, 3x plus 2x is 5x. We're going to add like terms. Here we have two brackets multiplying together. Lots of us call that a FOIL question. What it means in effect is that we have four products. One must multiply both terms and 2i must multiply both terms. 1 times 3 is 3. 1 times I is I. 2i times 3 is 6i, and 2i times I is 2i squared. Now we can simplify. 6i and I give you 7i. I squared gives you -1, so we end up with 5 plus 7i. Here we have a difference of squares. Same as m minus n, m plus n. The center term goes. So we end up with 3 squared minus 5i all squared. Give you 25i squared. And this we're squaring a binomial, which we can do by a pattern. We can write the two brackets separately and multiply out 4 product, but there is a system. Square the first, multiply the two together in doubles, so 6i doubled is 12i. Square the last, 4i squared. Now, I squared is -1, so we can simplify down to 5 plus 12i. Here are some exercises to try. Take away the brackets, add like terms. Multiply out your brackets. Your I squared is -1, so therefore we get plus 32. Four products, which then simplifies. Four products. (21i squared), which is minus 21 outside the bracket, multiply out the bracket. Difference of squares. Squaring a binomial. Square the first, multiply the two together in double, square the last. Multiply out the brackets first, giving that, then multiply by the 6. We have a difference of squares here, I squared minus 9, which we then simplify, and then we multiply by the I. This one, both the 6 and the I are being cubed, so we have 216i cubed. And I remind you that I cubed is I squared times I. There's a -1, making it negative. 3 brackets. Let's multiply out the first 2 brackets and simplify, and then we multiply out the remaining brackets. Straightforward simplification of I times I. Squaring a binomial. Two terms to simplify. Multiply out the brackets first, then by the minus 6i. This one has a pattern. You can either multiply out 2 brackets then again, or you may remember that x plus 1 all cubed is x cubed plus 3x squared plus 3x plus 1 by Pascal's triangle. So that's what I'm going to do here. I cubed, I squared, I, no I, 1, 3, 3, 1. Of course, the I cubed is -I, the I squared is -1, so giving you -3, and 3i plus 1 stay the same. And it simplifies to that. Squared, squared, square that bracket, square that bracket. Now it's the same thing being squared, which means now we have that being squared. And now we just apply the squaring method again. So in the same way that it is not simplest form to leave a third in the denominator, we like to rationalize the denominator. Complex numbers should not be left in a denominator. So we just multiply top and bottom by the same amounts to get rid of the I in the denominator. Note that I over I is really -1, so we're not changing the value. So it's I over I squared, and that gives us -I. So let's multiply top and bottom by 2 plus 3i, and whoops, we end up with an I on the bottom line again. So that's no good. So let's try and multiply by 2 minus 3i. Because you see, that's a difference of squares, which will square the 2 and square the 3i and give no center terms. So the i's are no longer there. And that simplifies to 6 minus 9i over 13. Now that looks pretty complex, but in fact, just get used to these. What it really says is rationalize the denominator and then split into 2 terms and you'll get your a and b. So I'm going to multiply by the difference of squares. There it is there. End up with that. Now because I want a plus bi, I'm going to separate it into 2 terms. And there's your a, there's your b. Here's some exercises to try. Notice in this first one, you don't need to multiply by 2i. Many will multiply by 2i, but it's unnecessary because the 2 will then cancel out again. This is negative 2, which I allocate to the whole fraction. I need to simplify the denominator first. There we are. That becomes minus 8i because this is 2 cubed is 8. I cubed is I squared times I. So I squared is negative 1 and we have the I. Once again, we only multiply by I over I. Now we have our difference of squares. Remember, if we multiply by 2 plus I over 2 plus I, we'll end up with I in the denominator again. Difference of squares, multiplication, remember that's really 1, so we're not changing the value. And this one we need to simplify the bottom line first. There we are, 3 minus 4i it becomes, and now we can multiply top and bottom by the same. Absolute value. Just as a little side issue, the absolute value of a complex number. That seems strange. But it stems, there's the complex plane. Now what happens is that we have a complex plane on which we put the numbers. The a's go here and the b's go here, remembering that b is multiplying I. So there's the point AB, and that represents a plus bi. Now, a plus bi, the absolute value is the distance of the point AB from the origin. So from there to there is the absolute value of a plus bi. So that's a, that's b. By Pythagoras theorem, that's the square root of a squared plus b squared is that distance. So that's why the absolute value of a plus bi is the square root of a squared plus b squared. So the square root of the absolute value of 3i, well, a is 0. And that makes sense because the absolute value, 3i on the plane will be at 3 here, which the distance from the origin will be 3. So we apply a formula, square root of 5. Simplify the product first, and now we can apply the formula. Equations with complex solutions. So x squared equals negative 9. In the past we will have said no solution. But in fact now we can, because x is actually plus or minus the square root of negative 9. Now we can separate negative 9 into 9 times negative 1, and we can square root the 9. So therefore plus or minus the square root of, plus or minus 3i. Plus or minus the square root of 9, which is 3, and square root of minus 1, which is I. So best way to do this is to take the 2 to that side and then square root both sides. Now the 5 can go to that side, and this can be separated to 2 times minus 1, so we'll have a square root of 2 separately. There we are, square root of 2 and minus 1, square root of minus 1i. This is quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now square root of minus 4, well, that's 4 times minus 1, so the 4 can come out. So minus 2 plus or minus 2i all over 2, and we can simplify that further, take out our common 2, cancel. X cubed equals 1. Now up to now, we've said, the only solution is 1. But in fact, degree 3 means that there are probably 3 complex roots. Sometimes there are more in some equations of different powers. So let's do that in a different way. Let's do that. Now, I hope you remember that there's a way to factorize that. It's called difference of cubes. X minus 1, then you square the first, multiply the 2 together, and change the sign, square the last. Now that gives us an answer, and we use quadratic formula on that one. And square root of negative 3 is root 3i. And there are 3 answers. Some exercises to try yourself. No plus or minus because it's already the positive square root. Square root of 8 can simplify to 2 root 2. Your calculator will do that for you, in fact. Now, very similar to the first, but we have to do the square root, which means we introduce a plus or minus. We introduce the plus or minus, and that's root 7i. Square root of minus 1, so therefore that's just I. The 2 goes across. So I've taken 27 to that side, negative 27. I've square rooted both sides, introducing the plus or minus. Square root of this just gets rid of the square root of negative 27. Now 27 times negative 1, and square root of 27, 3 root 3, and square root of negative 1, I. Quadratic formula. Square root of 32, 4 root 2. 16 times 2, square root of 16, 4. And this is the case where you need to bring the 8 across. Sum of cubes, there it is there. Square the first, multiply and change sign, square the last. And now we're going to say, well, negative 2 is an answer, and we're going to apply quadratic formula to that one. Three answers. And just to reverse the procedure, find an equation with roots 3 and negative 2. I say bygone days because this isn't part of complex numbers at the moment, but it's to remind you of a system. Equation with roots 3 and negative 2, so we can form the brackets x minus 3, x minus negative 2. Remembering, if the roots are x1 and x2, then an equation could be x minus x1, x minus x2. Notice it's an equation because there could be more than one equation with the same roots. Multiply out, there's our answer. So let's now apply that to an equation with complex numbers. Now notice x1, x2 means x minus, so we're going to do x minus, x minus 3 plus 2i, x minus 3 minus 2i. Now we're going to take away the brackets, then we're going to do something very clever. We're going to regroup this as x minus 3 minus 2i, x minus 3 plus 2i, because we have a difference of squares. That means that minus that plus that means we're going to have this squared minus that squared. So much easier to simplify like that. So therefore, x squared minus 6x plus 9, squaring that square, 2i, we'll get minus 4, and there's a minus. So there's our equation. One more. X minus, the two roots. Take away the brackets, regroup so we have a difference of squares. Now, we squared out the x plus 1, and root 3 squared is 3, r squared is negative 1, so it makes plus 1. And it simplifies to that equation. You have some to try yourself. X minus, That's why that's plus there, because x minus minus 2r. Oh, that's missing the 0. That should be a 0 there. 3 brackets, 5, x minus 5, x minus plus I, x minus minus I. That's how we get that. X minus. Now we've regrouped, so we have this difference of squares. X minus 1 all squared minus r squared. X minus. Regroup. We have our difference of squares. Simplifies. And x minus, regroup like that. Root 2 times root 2 is 2, r squared. And there's our final answer.